Hello, hello. Yeah, welcome to yet another vlog. Uh, there was a long pause. The last the vlog I did was about a week ago. I believe it was last Friday that I did the last one. I was quite busy this week, but I pushed myself to get back into the habit and finally finish Ziggling exercises. We are at exercise 108, if I can write it here. Yes. So without further ado, let's start. You've heard of while loops in exercises 11, 12, 13, and 14. You've also heard about switch expressions in exercises 30 and 31. You've also seen how labels can be used in exercise 63. By combining while loops and switch statements with continue and break statements, one can create very concise state machine. So we have an operator, one while switch statement, while true, switch. If up is 1, set up to 2, continue, comes back to the loop, 2 runs this, and 3 runs this, and then you return, else, and empty. This shouldn't happen, right? And then you have break. I'm wondering where this return will return to. This statement cannot be reached. Yeah, so this is going to be returning this, and this never happens. Also, I think this never happens, right? Because as soon as this starts, as long as the startup is 1, yeah, okay. By combining all we've learned so far, we can now proceed with a labeled switch. A labeled switch is some extra syntactic sugar which comes with all sorts of candy performance benefits. Don't believe me? Directly to source. Okay. Yeah, one thing I just learned, just like Python, Zig also has some Zen, and one of the interesting part is favor reading code over writing code. So that kind of explains why the documentation lags, because basically you should be able to learn it via reading the actual source code. So what I'm going to do, if I can copy what I want to, what happened? Please copy it. Yeah, now it works. So let's move this to this window. Faster tokenizer. Update the Zig tokenizer to use labeled switch statement. The benchmark and binary specs for itself. What am I looking at here? Zig new, zig old. Poop is the performance optimizer. Yeah, this is also developed by the creator of Zig, Andrew Cully. And then what it does, Zig old is to check and then new. What is dash D? Can I find it here without installing it? I don't know what is dash D's meaning. But what am I looking here? And there are wall time, peak rest, CPU cycles. This is benchmark 1. This is the result of this one, I believe. Yeah, this is old. This is the one that it's running the first time, and then Zig 2. Yeah, the same test with a new syntax, and then there is a delta happening. So peak RSS, whatever that is, it's the only dimension that's getting slower. The for the rest, I think it's already faster. Okay, this is I think I just need to trust it for now because those details I'm not aware of. But the program is running and the dimensions that we are checking there, what do they mean? I need to spend some time learning that. Anyways, let's not sidetrack. Here is the previous excerpt implemented as a labeled switch instead. So we have foo, which is switch, and then when we do continue, continue foo with number 2, continue foo, so we don't need an op anymore. And then when 3, it will return, and this will never be reached. Okay. The flow of execution on this second case is the switch starts with value 1. The switch evaluates to case 1, which in turn uses the continuous statement to reevaluate the labeled switch again, now providing the value 2. In the case 2, we repeat the same pattern as case 1, but instead the value to be evaluated is now 3. Finally, we get to case 3, where the return from the function as a whole, so the debug statement is never executed. In this example, since the input doesn't have clear exhaustive patterns and can essentially be any U8 integer, we need to handle all cases not explicitly covered by, yeah, that's fine. And what is Zig builds output? Wait a minute, I'm failing somewhere else. What happened? 76. Use of undeclared line 100. Okay, that's fixed. Went to 93. This is weird. I wasn't working for a week and probably somehow I decided to change something, and then something broke, and then yeah, it's fixed now. Back to our problem. I think 107 we also solved, right? Yes. What do you want to print here is, yeah, the content. Beautiful. Now we finally have the error of 108. Okay, here what's going on? We have a label switch, break expression, outside loop. Where to break to PR. And that should be like this. The pull request has been found rejected. So what's going on here? Oh no, your pull request keeps being rejected. How would you fix it? So switch, pull request draft, continue and review, continue to rejected, approved to merge, if rejected, return. Pull request merged. So I don't get it. Let's see what's going on here. The state I want to be in is merge. So I want to reach this here, right? And the only one that is exiting is this. Return to program, but can I? Let's see, is it possible to? Break to tree, return. Draft in review rejected. So I can fix this to get what I want. Yeah, but I wonder if that was expected to change. Anyway, let's consider that an answer. But my question was if I can break to outside loop, and that's not possible, right? You can either return or continue or break the pointer like this, which was happening. Yeah, probably that was the solution. Okay, 109 vectors. So far in Zigling, we've seen how for loops can be used to repeat calculations across an array in several ways. For loops are generally great for this kind of task, but sometimes they don't fully utilize the capabilities of the CPU. Most modern CPUs can execute instructions in which several calculations are performed within registers at the same time. These are known as single instruction, multiple data instruction. Okay. SIMD instructions can make code significantly more performant. To see why, imagine we have a program in which we take square root of 4 changing F32 floats. A simple compiler would take the program and produce machine code which calculates each square root sequentially. Most registers on modern CPUs have 64 bits, so we could imagine that each float moves into a 64-bit register, and the following happens 4 times. Notice that half of the register contains blank data to which nothing happens. What a waste. What if we were able to use data space instead? This is the idea at the core of SIMD. Most modern CPUs contain specialized registers with at least 128 bits for performing SIMD instructions. On a machine with 128-bit SIMD registers, a smart compiler would probably not issue 4 square root instructions as above, but instead pack the floats into a single 128-bit register, then execute a single packed square root instruction to do all the square root calculations at once. Interesting. Yeah, pretty cool. Code with SIMD instructions is usually more performant than code without SIMD. Zig cares a lot about performance, so it has built-in support for SIMD. It has a data structure that directly supports SIMD instructions, vectors. Operations performed on vectors in Zig will be done in parallel using SIMD instructions wherever possible. Defining vectors in Zig is straightforward. No libraries import is needed. Add vector, the size, I believe, then the type, and then the definition. Vector supports the same built-in operators as their underlying types. Interesting. Wait a minute, what have, oh, they are adding them together. Okay, v1 plus v1. Yeah, and then multiplication also happens. Is it possible to do matrix calculation like NumPy? Would be interesting. Intrinsics that apply to base types usually extend to vectors. Float from int, okay. And feature is this. They turn into a float. v4 minus v5. Yeah, and then absolute values. Okay, we can make constant vectors and reduce vectors. Oh, okay. This by reduce they mean a functional kind of reduce, right? Basically, with this, it's adding them together, and then here, taking the minimum. I wish LSP could pick up these definitions, but I need to look it up later on. Fixed length arrays can be automatically assigned to vectors and vice versa. Now let's use vectors to simplify and optimize some code. Ava is writing a program in which they frequently want to compare two lists of 4 F32. Ava expects the lists to be similar and wants to determine the largest pairwise difference between the lists. Ava wrote the following function to figure this out and calculate max pairwise diff old. So what's happening? We have two lists for F32. Max diff is 0 for list 1, list 2. We are in parallel iterating over them. Absolute diff, absolute n1 minus n2. If absolute diff is max diff, return max diff. Okay. Eva heard about vectors in Zig and started writing a new vector version of the function, but has got stuck. Help Eva to finish the vector version. The example above should help. So what we do here is do a minus b, and here that max. Correct me if I'm wrong. This looks correct. Zig build. Did I also do at absolute? I'm not sure. Yes, that was it. Okay. Quite simplification. We could even write the function in one line and it would still be readable. I kind of agree. Since the entire function is now expressed in terms of vector operations, the Zig compiler will easily be able to compile it down to machine code, which utilizes the all-powerful SIMD instruction and does a lot of the computations in parallel. This is interesting. Let's go for 110. Quiz time. Toggling, setting, and clearing bits. Another exciting thing about Zig is its suitability for embedded programming. Actually, this is my next step to discover. I found some interesting efforts to integrate this with Platform.io, which is an interesting platform developed for Arduino. I'm quite novice about I'm working on Arduinos, but I found Platform.io more in line my type of tooling compared to Arduino Studio. So yeah, interesting stuff coming up. But for now, let's focus on this. Your Zig code doesn't have to remain on your laptop. You can also deploy your code to microcontrollers. This means you can write Zig to drive your next robot or a greenhouse climate control system. Ready to enter the exciting world of embedded programming? Let's get started. Some background. A common activity in microcontroller programming is setting and clearing bits on input and output pins. This lets you control LEDs, sensors, motors, and more. In a previous exercise, bit manipulation, you learned how to swap two bytes using XOR operator, exclusive OR. Uh, this quiz will test your knowledge of bit manipulation in Zig while giving you a taste of what it's like to control registers in a real microcontroller. Included at the end are some helper functions that demonstrate how we might make our code a little bit more readable. Below is a pinout diagram of the famous Atmega 328 AVR microcontroller used as the primary microchip on popular microcontroller platforms like Arduino Uno. The pinout diagram, I actually have one Uno here. So, just to showcase what I see. Yeah, it's Atmega 328 P unit, the AVR controller. Drawing inspiration from this diagram, we will use the pins for port B as our mental model for this quiz on bit manipulation. What do they mean by port B? Pins for port B. Maybe PB is port B. Okay. It should be noted that in the following problems we are using ordinary variables, one of which we have named port B to simulate modifying the bits of real hardware registers. But in actual microcontroller code, port B would be defined as something like this. Volatile U8. We never learned about this type. This lets the compiler know not to make any optimizations to port B so that the I/O pins are properly mapped to our code. To keep things simple, the following problems are given using type U4, so applying the output to port B would only affect the lower 4 pins PB0 to PB3. Okay, this and this 3. 14, 15, 16, 17. Of course, there is nothing to prevent you from swapping the U4 with U8, so you can control all 8 of port B's I/O pins. Okay, what is the error? We have some question mark. We have print and testing in. Port B is a U4. In binary, we are setting all of them to 0. See if you can solve the following problems. The last two problems throw you a bit of a curveball. Try solving them on your own. If you need help, scroll to the bottom of main to see some in-depth explanations on toggling, setting and clearing bits in Zig. Toggle pins with XOR on port B. This is port B, initial state of port B, and then bit mask is that. Okay. What's wrong here? We are shifting So port B would be 1110. Okay, let's first make it compile. There is 9106. Set port B. This is kind of cryptic. What are we trying to do here? We are resetting port B. Set pins with OR on port B. Okay. I'm just guessing my way through it. What character is missing here? I saw an example up here. Nothing specific. Just going to do this, picking up from this. What is missing? I have no idea. Okay, this was the most confusing exercise ever I've done. But let's run it. What's missing here? Okay, now it's better. So let's drink a sip of water. What are we looking for here? Is initial state of port B. What do you want? You want to preserve this? You want to preserve this? Okay, this is XOR. This is supposed to be XOR, right? And what are we doing? Now we are getting 4-1. How does it work? Let's do something. We'll print down here to 1, shift 1, and then 1, shift 0, D here to binary. Yeah. What did I print here? So this will become 2, this will become 1, right? And when we do that as OR, we will get 1, 1, right? And then if we do 1, 1, 0, 0 OR together, we will end up with 4, 1. Okay, now what I want to do is to set, let's see, if I do this, I'm going to set 1 bit correctly, I hope. Still no. Okay, what we need to present here is this value, right? And then if I want to set this, this should be 2. And this should be 0. Yeah, that worked. It took me some time to realize what's going on in the log. Okay, now the next one, incorrect, we want all 1. So what we want to have is 0, 0, 1, 1. Now I'm getting 2 bits, right? And what I need again is to make this. What it is doing 10. Oh, it's and here. Woohoo! For the rest, it was correct. Okay. Let's go through this description because I'm not that solid. I did some guesswork, but eventually I think I figured it out. But let's do this. XOR stands for exclusive OR. We toggle bits with the caret and then bitwise operator like so. Yeah. In order to output a 1, the logic of an XOR operation requires that the two input bits are of different values. Therefore, 0 XOR 1 and 1 XOR 0 will both yield a 1, but 0 XOR 0 and 1 XOR 1 will output 0. XOR's unique behavior of outputting a 0 when both inputs are 1s is what makes it different from the OR operator. It also gives us the ability to toggle bits by putting ones into our bit mask. Ones in our bit mask operand can be thought of as causing the corresponding bits in the other operand to flip to the opposite value. Zeros cause no change. Cool. These zeros in the bit mask preserve these values in the output. Yeah, this bit is already clear. We can think of these bits having flipped because of the presence of ones in those columns. That's too much description for this concept. Setting bits with OR. We can set bits with on port B with the OR operator like so. These bits remain untouched because ORing with a 0 affects no change. Okay, to create a bit mask like 0010, use above. And this allows us to write clearing bits with not and and. That's what I did above. For not, it's using tilde. And then we can use, yeah. For more insight into Zig's position and why the language takes the approach it does with tilde operator, take a look at Andrew's comment, the following GitHub issue. If you define tilde x as minus x negative x minus 1, then you now have the question of whether this should work. Without any further changes, okay, in my opinion, this actually is more confusing since you can't do. Okay, this is. I think they're favoring in readability and flexibility of the operator. This also makes sense. I've seen still being used like this in other languages as well. So no much problem there. Conclusions. While the examples in this quiz have used only 4-bit wide variables, working with 8 bits is no different. Here's an example where we set every other bit beginning with the 2's place. Yeah. Here we clear every other bit beginning with the 2 place. Here are some functions for manipulation bits. Set bit, clear bit. Yeah, interesting. I'm also finding the availability of tests quite useful. I was working on Code Crafter Challenge, and I realized when I get deep into implementation before running my code, I usually end up spending a lot more time fixing the errors I make when I'm trying to compile something. So I'm thinking maybe I need to utilize running tests before actually I'm using the methods, function, classes, modules, whatever I'm building. And then only when I'm stable with something, then use it in the main function. Probably it will speed up my progress. But that I will try to practice more, of course, on the stream as well. I have some plans to build some stuff from Code Crafters live in this channel. Hopefully that will give me more insights on my workflow on Zig development. With that being said, I think we are finished. This is the end for now. We hope you have had fun and were able to learn a lot. So visit us again when the next exercises are available. I, to be honest, really enjoyed the exercises. I'm not sure how much of this knowledge I preserved, probably less than I expected. But this was a good warm up for me. So when I try to code in Zig, which I did today, I think I remember some stuff. So I don't know the exact syntax, but I remember some stuff. I can get back to my Ziglings and find what I was looking for, and then that reinforces my learning. So that's quite useful. With that being said, thanks for watching. Feel free to leave your feedback or your guidance to help me here, and see you in the next one.